So we're going to have to do a few things in order to be able to see what our numbers look like. So we're going to modify our main program just a little bit. So here we have our main.c, and what we want to do is, instead of saying that this returns an int, we're going to say that this returns a double. The result of that is that the result will be returned in XMM, which is one of our registers that we can use for that. And so we're also going to change this. So this is a double. So ASM main is going to be called, and it's going to return to us a double, or a floating point number. So we can go ahead and print it. Say the value is, we'll do %f, and then we're going to do return status. Now we also have to include standard IO. So that way we can do our print that we want to do. All right, so now the way that the floating point works is that it actually uses a separate processor. They call it the x87 instead of x86. So the x87 processor, and that allows us to do these mathematical operations. So if you guys are interested, you can go look at the x86 floating point or x87 coprocessor in order to sort of understand a little bit more about how that floating point works. But we'll just go through it today, and hopefully it makes a little bit more sense. So the second thing I want to show you is that, so floating point, here's another website which will convert a hex number into a floating point number. So we can see that in this diagram, there are 3 different parts of our floating point number. The very top part is our sign bit. It says whether or not this is a positive or a negative number. We then have some number of bits. In this case, it looks like it's 4, 8, 9, 10, 11 bits that are the exponent, which means if this is going to be a really big number or a really small number. And then the rest of our bits are showing the actual values that it's storing, right? So it's storing that in binary. You're assuming that the number in binary is 1 point and then a whole bunch of bits, right? So there's an extra assumed 1 at the top because there's no use keeping any zeros at the top. So in order to make it as efficient as possible, it starts 1 point whatever. And so then you're taking your Mantis and then you're multiplying it by this exponent in order to get the floating point result. Now the way that the floating point processor works is it has its own stack where you can push on multiple values in order to use them. So let's define a few values inside our program. So we got A, we'll define it as a keyword, and we're going to pick the number 4.0. So that will, in that representation that we just saw, that will store it inside of our binary so that we can be able to use it. In addition, we'll do A as an int. So we'll just use, for an integer, right, we can actually load them onto the floating point stack and then use them. So we can use an integer if we want. I have another one called B. So it's going to be, say, 7.1. And here's an integer that is 11. And then we got our result here that we're going to use. And we'll just define it as 0 to start. So at the sort of end of our program, if we have our result wherever that may be, we can move that into the XMM register, which is what C expects the result to be. And so instead of RAX, it's XMM0. So we can do a move Q XMM0, which is a 128-bit register. We can get our result. So again, res is going to be the result that we have. So I should be able to save this, do a make, and our result is 0, right? So We indeed did return it. If I picked a different number for res, say 1.0, we can see that our result is 1. Right, so we know that this now works. Right, so this is taking that value at that location relative to RSP and then storing it in XMM0, and then main.c is going to take that result and put it into the variable that we call ret status. All right, so let's do some floating point. So you don't necessarily have to do this, but this is probably best practice. So the fn init will initialize the floating point stack to say that you're ready to do things. And then you can basically start loading things. So if I do FLD, so floating point load, I can't just do a move. I'm going to do a keyword, and I'm going to get the value of A. So again, we'll just do some examples here and go from there. So I can also load keyword, the value of B. And then again, floating point has their own things. So I can say f add, and then the way the floating point stack works is that the first thing that gets put on there is at st0. So that's the first register. The second one is st1. I believe there are 7 of them. So we got st1 through st7. And when you do an operation, it's going to take the 2 things that are on top of the stack and then do that operation and then save one of those. So if I say fadd st0 st1, it will add it'll pop them both off, st0 and st1, and then save the result in st0. So that allows us to do our add. We then have to be able to pull this thing off of that floating point stack. So we can say fstp or floating point store to a pointer, so we can store a keyword res. So that should take our result and then save that to res. And then we can load res back and return it from our function. All right, so A is 4, B is 7.1. If you add them together, you get 11.1. Right, so that's our result. Now there's also a couple other things. So with this fadd, if you just give it no arguments, and then we run our project, we get the same result. So it does the pop of both of them and then save them. So essentially that was doing the same operation. Additionally, we don't necessarily have to load a floating point number. So for example, we can do floating point integer at load, and then we can load in a keyword. And let's get b int. So if we load that in, sorry, let's use A. We'll use A's int, not B's. Let's do A. So this is the second one, so 4 plus 3, so we should get 7. So that will take that integer and it'll convert it into a floating point. So we'll go ahead and save. And we can see here that we didn't quite get the result that we wanted. Now, that's because when we did the integer, we said it was a keyword, but aint is not a keyword. So what we need here is we need to say that aint is a D word. There we go. 4 plus 3 is 7. So understanding, what size of integer it was loading, right? So it was actually loading more data than just this when you said it was a keyword. And so we have to make sure they align. Now, the B one, right, is a keyword. So if we wanted to do that one instead, FILD keyword B int. So now that's A plus B's int. So we got 4 plus B is 11. So that gives us 15, right? And additionally, you can, if you're going to do an integer, right, there is another instruction where we could say instead of that, floating point I add instead of f add. So we can do an integer add of the keyword b underscore int. And what that does is that takes that integer, it does it loading it into the floating point unit and then adding it onto the thing as at st0, which is on top of the floating point stack. Oh, I think in this one, let's see. Oh, I add, I think, has to be a D word. So let's use a. So here we're going to go ahead and add those two together. And we get the result that is 7. Right? So we had our a and our a int, so 4 and 3. We just go ahead and directly add it. Now it's on top of the stack, so I don't have to do a separate instruction for loading. And I can go from there. So this is not all of the floating point operations that you can do. If you are interested, you can go and look at the manual for some different functions. Right? So there are a lot of different floating point functions that we can see inside of here. So we can see that there is a cosine, subtract, square root. Right? So a lot of the different operations that you're going to do, right, are in this list of what are all the floating point operations. So this video is just to give you an introduction to it, but it's not going to be the end all be all of floating point. So hopefully that helped make sense of the different floating point registers and how we can use them, and then what the type of format is used to store them, and how that floating point stack works. All right, thanks guys. We'll talk to you later. Bye.